Everyone, welcome back to another video about physics past papers. Today we're going to talk about the variant 4.1, which is the A-level structured question, the A2 structured questions paper from the May-June 2025 series. Before we jump into the paper, some resources that we have developed for the entire A-levels. This is already neatly packed into the Patreon page as a grade booster. The link also is in, as you can see in the video and in the description. Up till now, it contains 8 documents. As you can see, definitions and formulae for AS, important definitions and important key points, important formulae as the name suggests, frequently examined questions. Currently, this contains paper 2 questions. We're also working to include some frequently examined questions from paper 1. Then we have AS derivations. Some of them are very important, some of them are for learning exercise. Now for A2, since this is paper 4, now is going to be more important for you to see what we have done over here. So this is the frequently examined questions document. As you can see on the left side, you have syllabus points. The following columns are question, answer, and the year. So questions are arranged and organized based on the syllabus points. The answers are marking schemed aligned and examiner reports aligned. The years over here show how frequently you can expect to see these type of questions. Where you see a lot of years, that means they're very likely to come in the exam. Then we have A2 definitions and formulae, which is very similar document to what we had for AS, key points, important definitions. Important derivations, we know we often get this derivation, this one, some form of this one, and the rest also. As a learning exercise, we know we get the capacitance ones also, so it's all we have written with explanation. Then we have graphs. We know we struggle with field and potential graphs, so they're all there along with the rest of the chapters also, including the simple harmonic motion, these energy and the velocity, angular velocity graphs, thermodynamics graph, and quantum physics graphs, and so on. Last but not the least, we also have the paper 5 planning question checklist. This checklist is based on the requirements of the syllabus, the exam paper itself, and the examiner reports. So what are we expected to remember? What are we expected to write? Everything is there. And we also have some solved examples from the 2024 October one. So over here you can see what details, how thorough you can be to in your experiment design. Now, this is all currently packed into the Patreon page. Again, the link you can see in the video at the bottom. So go ahead, check this out. And let's move on to the paper. Okay. Define gravitational potential at a point. Now, this definition is easy. However, just to show you that we have got you covered in this gravitational potential. Define gravitational. Sorry, wait. Oh, my bad. The question that we had was define gravitational at a point. Okay. So define gravitational potential at a point. Gravitational potential is the work done per unit mass in moving a mass from infinity to that point, exactly as it is. And not just that, this is also in the definitions and formulae document also. So if you see this over here, somewhere, gravitational potential at a point in gravitational field is defined as the work done by gravitational attraction to bring a mass from infinity to that point. So whichever one you prefer, this one is more concise and better. So work done per unit mass in moving a mass from infinity to that point. So we can say it is defined as the work done per unit mass in bringing it from infinity to that point in space. And that's it. Okay. Mars is a planet that can be considered to be isolated uniform sphere of radius 3.4 10 raised to power 6 meters. Okay. Satellite of mass 122 kg is in orbit around Mars at a constant height of this above the surface of the planet. The height of the orbit is increased to this above the surface. This increases the gravitational potential energy of the satellite. Now, show that the mass of Mars is this. Okay, so when we're dealing with the satellites, so remember, in case of satellites, we have to remember the energy exchange between kinetic and potential. So potential energy has the same formula, Gmm over R. Kinetic has half Gmm over R, and the total energy would be minus half Gmm. Let's see how much we actually need from this. So we need to show the mass of this. So what information is given? Previously, at a constant height was this. Now it is increased to this. Similarly, this is the radius. Now, why is it important over here? So the distance, sorry, the r that we're talking about in the formulae, that is from center to center distance. So that r that we keep using in the formulae, gmm over r or something, that is not the height above the surface, it's actually this one. So this is the height. So we need to be able to add those distances first. So first off, we need to know the R before. Let's say R1. R1 is 3.4 10 raised to power 6 plus 1.7 10 raised to power 6. Then R2 is R1, oh sorry, increased to this. Okay, so from the radius 3.4 10 raised to power 6 plus 6.8 10 raised to power 6 meters. Okay, so now the distances from center to center. So 3.4 plus 1.7, that is 5.1. So 5.1 10 raised to power 6, and this is 3.4, 6.8. This is 1.02 or 10.2. So you can do 10.2 10 raised to power 6 or 1.02 10 raised to power 7, however you wish to proceed with this. Okay, now similarly we need the potential energy before, potential energy after. So EP initial, we had half GMM. Actually, you can do the minus half GMM also, but at the moment we just need to know the change in this. So GMM over R1 or initial. So you could also do this as initial and final, basically. So when we include this, sorry, my bad, we don't need the half over here, right? Right. That for potential we don't need that, my bad. For kinetic we need that. Okay. So GMM for G, we can keep G We know the G value, right? Sorry. We can bring it a little bit here. Right. So G is 6.67 10 raised to power minus 11. M is unknown. Small m, which is the mass of the satellite, is known. And this is 5.1 10 raised to power 6. EP final is again GMM over RF. 6.67 10 raised to power minus 11. M 122, but now the radius is 10.2 10 raised to power 6. Okay, so let's quickly just calculate these. So 6.67 times by 10 raised to power minus 11 times by 122, 5.1 10 raised to power 6 minus 6, sorry 6, just 6. So we get this value. So 1.595, let's do 6, 10 raised to power minus 15 joules. And this one, there's only one change, 10.2, 7.9778, 10 raised to power minus 16 joules. Okay, so now we know that the, sorry, we need to multiply the G also. So, sorry, M, J, M, joules. Okay, so the change in potential energy they have given us as 5.1 10 raised to power 8. So the change in energy, so 1.5956 10 raised to power minus 15 minus 7.9778 10 raised to power minus 16 times by M equals to 6.8 10 raised to power 6. Oh, sorry, no. It's the other way around. 5.1 10 raised to power 8 joules. Okay, so now for the M, we just need the difference and divided by, sorry, 5.1 divided by the difference. Okay, so 5.1 times by 10 raised to power 8 divided by the difference between 1.5956 times by 10 raised to power minus 15 minus 9778 times by 10 raised to power minus 16. So we get 6.392 10 raised to power 23, which is exactly almost what we needed to find out. So yes, that would be 6.4 10 raised to power 20. That's it. Okay. Calculate the gravitational potential phi at the surface of Mars. Okay. At the surface of Mars. So basically what we can do is, see, this time we need the potential. So we can have it as negative this time. So phi is equal to minus gm over r. So minus 6.67 10 raised to power minus 11. Mass is 6.4 10 raised to power 23 divided by the 3.4 10 raised to power 6. Right, okay. So 6.67 times by 6.4 divided by 3.4 times by 10 raised to power minus 11 plus 23 minus 6 we get this value. So 1.255 10 raised to power 7 joules per kg. So this would be 1.3 10 raised to power 7 joules per kg. Okay, all right. Let's see further. The satellite in B is moved to an orbit in which the satellite remains at the same point above the surface of Mars. We're talking about the geostation. The orbit has a period of 25 hours. State what can be deduced from this about the rotation of Mars on its axis. Now we know what it means. So the period of the geostationary satellites is usually equal to the period of the planet itself. So on the Earth, period of the geostationary satellite is 24 hours, which is also the period of rotation of the planet. So basically, that's exactly what we wrote. So the period of rotation of planet Mars on its axis is 25 hours. State one feature of this orbit. Now, usually the the geostationary satellites, they have certain features. Orbit time is 24. This is just for Earth, by the way. So we have already discussed on Mars it will be 25. Over equator. So over equator, uh, that will be true for the Mars satellite also. Satellites go from west to east. Again, this is just specific to Earth. So whatever the direction of rotation of satellite whatever the direction of rotation for Mars is, whether it's east to west or west to east, that will be the same uh, direction for the satellite. So we can say the orbit is above equator. Okay, so state one feature. Any one of those, you could also say direction of rotation or direction of orbit. So direction of rotation is the same as direction of rotation of the planet. That's it. All right, moving on. A helium atom may be modeled as a nucleus surrounded by two electrons in diametrically opposite circular orbits. Okay, so diametrically opposite means that these electrons, they are literally opposite to each other at a diameter's length. Okay, state Coulomb's law. Again, Coulomb's law is very similar to the gravitational law. Okay, state Coulomb's law. Coulomb's law states that the electrostatic force between 2 point charges, again, the keyword over here is point charges, is directly proportional to the product of the charges and inversely proportional to the square of the distance between. So we can say that it states that the electric force between 2 point charges is proportional to the product of the charges and inversely proportional to the square of their separation or distance between, whatever you want to call it. Now, state the charge on the nucleus in terms of the elementary charge. Okay, so first off, we know that this is a neutral atom. So the total charge on the electron would be also equal to the total charge of the protons in the nucleus. But again, opposite charge. So that would be just 2e plus 2e. Show that the electric force between the nucleus and one of the electrons is this. Okay, so for force, we can say this is K, Q, Q over R. So K value, you can see in the, this is going to be 8.99 10 raised to power uh, minus 9, but let's see. Sorry, 9, positive 9. 8.99 10 raised to power 9. Okay, my bad. So 8.99 10 raised to power 9. Charge on the nucleus is 2. We will write the E later on. And charge on electron is 1 times by 1.6 10 raised to power minus 19. This is the fundamental charge. Then we have the radius is the radius given. Radius is given in picometers, 170 pico. So pico is 10 raised to power minus 12. So 170, 10, sorry, this is squared. 10 raised to power minus 12 whole square. So 8.99 times by 2 times by 1.6 divided by 170 squared times by 10 raised to power 9 minus 19 plus 24. We get this value. Oh no, wait. There's some problem over here. KQ Q over R squared. Oh, sorry, this would be squared also because it's 2e and then 1e. So this would be squared also. So 1.6 squared and the 19 also minus 19. So, okay, now it is clear. Okay. So this would be 1.6 10 raised to power minus 8 because this was 2e and 1e, right? So e and e would come out twice. So newtons. Okay, all right, moving on. Assume that the force in V2 is the only force on the electrons. Calculate the speed of the orbiting electron. So we can use the circular motion rule. F is equal to mv squared over r. So v squared would be fr over m. Force we just found out to be 1.6 10 raised to power minus 8 newtons. Radius was 170 10 raised to power minus 12 meters. Mass of the electron, we need to go and see again for the mass. That is 9.11 10 raised to power minus 31. So 9.11 10 raised to power minus 31. Okay, so square root 1.6 10 raised to power, 170 divided by 9.11, 10 raised to power minus 8, minus 12, plus 31. We get V to be 1.727 10 raised to power 6, which would be 1.7 10 raised to power 6. Calculate the period of orbit of electrons. So if we have found out V is equal to R omega. Omega is basically 2 pi over T. So we can rewrite this as T would be 2 pi over V over R, basically. So 2 pi over omega, and omega is V over R, basically. So that's what we would do. So 2 pi divided by speed is 1.7 10 raised to power 6, divided by R was 170 10 raised to power minus 12. So this is coming out to be 6.283 10 raised to power minus 16 seconds. So 6. Let's say 3 10 raised to power minus 16. Okay, moving on. In practice, the orbit of each electron is affected by the presence of the other electron. For the position of one of the electrons, determine the ratio. Electric field strength due to the other electron and electric field strength due to the nucleus. So electric field strength, we know that this is just kq over r squared. So in the ratio, k and k would be basically cancelled out, and obviously the values of charges would also be different. So what we have over here, so we have basically q1 over r1 squared, q2 over r1 squared. Okay, so q1, which is due with the other electron, so 1.6 10 raised to power minus 19. The distance to the other electron is full diameter away, so 170 times by 2 times by 10 raised to power minus 12 whole square. Ratio 2 times by 1.6 10 raised to power minus 19 divided by the distance to that is 170 10 raised to power minus 12 whole square. Okay, so as you can see, we can cancel out a few things. So 1.6 gets cancelled. This ratio gets cancelled like this. So we are left with 2 squared at the bottom and the other that way. So 1 ratio 8, which is basically 0.125. So you could write it as 0.13. Okay, so how I went from over here, just if you feel that I made a jump over here, this is 1 over 2 squared, which is 4, and this is 2, so this is simplified as 1 ratio. Okay, this was straightforward, but okay, let's do it. All right, use your answer in D1 to suggest and explain how the orbit of the electron is affected by the presence of the other electron. So to understand that, we can go back and see the resultant force over here. So the force due to the nucleus on the electron is this way, right? And the force on the nucleus due to this electron is Fe. However, due to this electron, let's call it E2, since they're similarly charged, it's going to repel. So this is the Fe2, you could say. Now, normally, what we are expecting over here, the sum of forces is the force due to the nucleus, which is the kq over r, which we figured out multiple different ways over here. Yeah, electric force between that, right? This is that. And we have to subtract the force due to the electron also. So the net force, the resultant force, is less than what we actually calculated over here. So due to that fact, see how it's changing or affecting the speed and the orbit. So first off, how it's going to affect the speed. If force is lower, the speed would be lowered also. So if force is lowered, the net effect would be that the speed is lowered. When the speed is lowered, the time period would be greater. So that's what we have to suggest. How the orbit. So how the orbit, we could explain it in terms of speed or period. So the net force on an electron is lower than that, sorry, lower than force between electron and nucleus, which reduces orbital speed and increases the period, orbital period. That's it, simply. Okay, all right, moving on. Define specific latent heat. Okay, and the second question, look at it. Explain why for a substance, the specific latent heat of vaporization is usually greater than the specific latent heat of fusion. Now, again, these two are very frequently examined questions. So we go back to the thermodynamics, sorry, temperature. Where did it go? Okay. State what is meant by specific latent heat, amount of energy required per unit mass to change the state of substance without changing its temperature. The other one, specific latent heat of vaporization, is greater than the specific latent heat of fusion. Now, there are two ways the question could be asked in terms of spacing of molecules, and there was another way which we wrote somewhere below. This was with reference to internal energy. Explain in terms of internal energy. So whichever way you, since the question that we are facing in the 2025 paper is not specifying what we need, how we need to explain it. So we can explain it in terms of spacing, and we can explain it in terms of internal energy also. So how you can explain both ways? Let's see. Vaporization not only involves breaking of intermolecular bonds, but also increasing the spacing between the molecules to a much greater extent. That means the spacing of the molecules is increasing to a greater degree, then in case you want to go this way, uh, larger increase in internal energy requiring more energy to break intermolecular bonds and intermolecular spacing significant. That means that since the kinetic energy is since the temperature is the same, kinetic energy remains the same. So that's the you you could use this thing very easily. So since, oh sorry, first we need to write this. So this is going to be the amount of thermal energy or heat required to thermal energy per mass, per unit mass, required to change the state of the substance at constant temperature. The constant temperature is an important key point that if you miss out, you might lose one mark. Okay, now we need to explain this, that the vaporization involves not only breaking of intermolecular bonds, but also increases separation of molecules greater than fusion. Therefore, more energy is required to break the bonds and increase separation of molecules. This causes an increase in, you could say, increase in internal energy of molecules, or you could also say potential energy of molecules. Uh, Remember that the kinetic energy of molecules is constant. Why? Because we are doing this at a constant temperature. Okay, an ice cube of mass 37 grams at a temperature 0 degrees Celsius is placed in a beaker containing water of mass 208 grams at temperature 26.4 degrees Celsius. When all the ice has melted and all the water in the beaker has reached thermal equilibrium, the final temperature of the water is 10.3 degrees Celsius. The specific heat capacity of the water is this. The beaker has negligible specific heat capacity and is perfectly insulated from the surroundings. Determine a value to three significant figures for the specific latent heat of fusion of water. Okay, Now, to understand this, we need to remember that the energy extracted by ice and the ice water temperature change is actually coming from the water in the beaker. So energy gained by ice is actually coming from energy lost from water. So the energy gained by ice is actually two things. It's one is the latent heat, let's call it Mi for ice, plus the mc delta theta for ice. Okay, and the energy lost from the water is also mc delta theta, but this is water and this is for ice. The specific heat capacity that we're going to use is going to be the same, because once the ice has converted into water, then the temperature change will happen. It's not ice uh, specific heat that we have to use. Now, let's use the numbers over here. So first off, the ml, latent heat, we actually need to find that out. Huh? So the ice cube is 37 times by L plus 37 grams. Actually, okay, so this is given as joules per gram, so we can use grams over here. And also Celsius, so we can use Celsius. 37 times by 4.18 times by change in temperature for the ice is 10.3 minus 0. So 10.3 minus 0. From the other side, now the water. So water mass was 208 grams. Specific heat capacity is 4.18, and change in temperature of water was from 26.4 to 10.3 degrees Celsius. Now all we have to do is to find out L. So this is 37L plus 37 times by 4.18 times by 10.3. This is, we can keep it as it is. We can keep it as, sorry, oh, my bad. So 208 times by 4.18 times by 26.4 minus 10.3 minus 37 times by 4.18 times by 10.3. Now we have figured this out. So 37L would be 1.2404986 10 raised to power 4. So L would be this answer divided by 37. So we get 3.352, 335 basically. 0.2 joules per kg. So this would, sorry, grams basically. So this would be 335. Okay, all right. Moving on to the fourth question. Okay. State what is meant by an internal energy of a system and explain why the internal energy of the gas, ideal gas, is directly proportional to the thermodynamic temperature of the gas. Both are easy and again frequently examined questions. So to understand this, first off, the internal energy is the sum of kinetic and potential energies of its particles. Okay, so it represents the total energy of the particles that make up a substance, including their random motion, and interactions with each other. Okay, so sum of potential and kinetic energies representing their random motion and interactions with each other. Now, the second question was that what was it? Sorry. Internal energy of an ideal gas is directly proportional to the thermodynamic temperature. So this is going to be in the ideal gas part, I guess. Okay. So you see over here, these 2 points over here. So by referring to both kinetic and potential energy, explain what is meant by internal energy of an ideal gas. This is explained, the question answer that we're looking for is explained over here. And so internal energy is the sum of random kinetic energies of its molecules plus the total potential energy. But however, since there are no internal molecular forces in an ideal gas, potential energy is zero. So internal energy consists only of kinetic energy. Now, the other point, its temperature is related to the average kinetic energy of the particles. As temperature increases, particles move faster, which increases the internal energy of the object. So somehow we need to merge this into this. So first off, so it is the sum of kinetic and potential energies of the particles of the system. It is the total energy of the system representing the random motion, random motion of particles and their interactions with each other. Okay, explain why the internal energy of an ideal gas is directly proportional to its thermodynamic temperature of the gas. So 2 points we can say that. So we just saw those 2 points over here. Since there are no intermolecular forces in an ideal gas, the potential energy is in ideal gas is zero. So internal energy is equal to total kinetic energy. Now we need to explain that the total kinetic energy or kinetic energy is proportional to the thermodynamic temperature. So kinetic energy of particles kinetic energy is proportional to thermodynamic temperature. So therefore now we need to connect internal energy with thermodynamics. So internal energy is proportional to temperature. thermodynamic temperature. Okay, a sample of an ideal gas at a thermodynamic temperature T has internal energy U. This gas is compressed, so its temperature increases to 3T. That means the kinetic energy is increased proportionally. During this compression, work W is done on the gas. The gas is then cooled at a constant volume so that its temperature decreases to 2T. Complete table 4.1 to show in terms of all W, T, and U, the work done on the gas, the thermal energy supplied to the gas, and the increased internal energy of the gas for each of the two processes. Okay, so we know that U is equal to plus Q and plus W. So the change in internal energy is coming from the sum of thermal energy supplied to the gas and the work done on the gas. Okay, so first off, what do we know from this? It already has internal energy U. The gas is compressed so that its temperature increases to 3T. Okay, so what else do we know? During this compression work done, the gas is then cooled at constant volume. So when it is done at constant volume, so zero work is done on the gas. Okay. Right. What else do we know? Oh, right. Sorry. So it increases to 3T from T. So we already said that the internal energy is proportional to the thermodynamic temperature. So the change in temperature also will reflect the change in internal energy. So change in temperature or change in kinetic energy is proportional to change in temperature, and which is proportional to the change in internal energy. So change in temperature is 2T. So that means that the change in internal energy will be 2U. Okay, so it's reflecting that change. So this is going to be plus 2U. Now thermal energy supplied to the gas. We need to figure out this one. So for Q, we need to do U minus W. So that is 2U minus W. So 2U minus W. Again, where is this coming from? We already discussed that the kinetic energy component is coming from the thermodynamic temperature. So when the temperature increases by 2T, the kinetic energy component, which is directly proportional to the internal energy component, also increases by double. So that would be a similar change. So it would increase to 3U. So that means the change itself would be 2U. Okay, now we are decreasing the temperature to 2T. That means we are going from 3T to 2T. So change in T is actually just simple T. That means from 3U, we are coming back to 2U. So increase or change in internal energy would be just simply minus U. Now we need to figure out the thermal energy change. So thermal energy Q is equal to, U is equal to plus Q plus W. So the work done part is 0. Change in internal energy is minus U. So Q would be also minus U. So that's it. Straightforward. Okay, all right. A cuboidal block floats in a liquid with its base horizontal, as shown in figure 5.1. The base of the block is at a depth h below the surface of the liquid. The block is displaced downwards by a small distance and then released so that it oscillates. Figure 5.2 shows the variation with height h of the acceleration a of the block. Okay. Figure 5.3 shows the variation with h of the kinetic energy of the block. Right. Determine the amplitude of the oscillation. So amplitude is basically from this to this. This is the mean point. So this is going to be 1.4. So 0.6, 0.6 will be the amplitude. So 0.6 meters. Okay. State what the line in figure 5.2 shows the nature of the oscillations. This actually shows that the acceleration is directly proportional to displacement, or it actually shows basically this thing, that the acceleration or the motion of the block is simple harmonic. That the they said nature of the oscillations, that the oscillations are simple harmonic. Okay, state three other qualitative conclusions. Now, qualitative conclusions that doesn't necessarily rely on the numbers, doesn't necessarily. That can be drawn from figure 5.2, 5.3 about it, the block and its oscillations. Use the space for any working. Okay. So first off, we have already deduced that the oscillations are simple harmonic. Okay, so let's see what else can we do. Okay, so first off, so what we can examine from this, there are a few things we can examine. So we know from the graph, actually, I'll just show you the graphs of kinetic energies. So, sorry, the simple harmonic motion. Right. First is this one. Okay. So the points over here, these points are actually corresponding to the ones that we saw. So the y value is omega x naught squared, omega squared x naught. The x coordinate represents the amplitude, and the y part, the maximum acceleration, which can give us omega if we have the acceleration, which we have. Secondly, the kinetic energy graph. The kinetic energy graph is the red one over here. This can tell us the mass. So when it is at the maximum displacements, kinetic energy is zero. But when it is at equilibrium points or the mean positions, the x is zero. So that can give us the maximum kinetic energy, and maximum kinetic energy can give us the mass. Okay, so from omega we can get frequency, time period, and we with kinetic energy we can get mass. So these are two easy descriptions that we can easy information that we can actually get from the graphs. Okay, so first off, we know that this is the highest value. This is going to be 0.9. So 0.9 is the omega squared x naught. So x naught is 0.6, not 0.8. So omega squared would be 0.9 over 0.6. That means just 9 over 6. So 9 divided by 6, that is omega is 1.225 radians per second. So if omega is this, time period would be 2 pi over omega. So 2 pi divided by answer, that is 5.13 seconds, and frequency would be 1 divided by answer, so that would be 0.1949 hertz. Okay, so this is what we can get from that. So second thing, now we need the mass. So maximum energy is also 9 joules. Okay, so you can see this over here, 1, 2, 3, 4, 5, and this would be 9 joules. So total energy, kinetic energy, maximum kinetic energy is half m omega squared x naught squared. So maximum kinetic energy is 9 times by 2 divided by mass. Sorry, mass we need to find out. The omega is this 1.225. Right, okay. So omega is 1.225, or sorry, omega squared was 9 over 6. Omega squared was just simply 9 over 6. X naught squared is 0.6 whole square. Okay, so 9 times by 2, 9 divided by 6, times by 0.6 whole squared, that is our mass. That is 33 kgs. 33.3 kgs. Okay? Okay, so I think these would be enough. So we have to write the workings over here. Okay, so maximum acceleration is 0.9. You could say meters per second squared also, because the acceleration is still, you know, omega squared x. Omega is 2 pi over t, so 1 over second squared meter, so meters per second squared. That gives angular frequency as we actually found angular frequency omega 1.225 radians per second. Time period equals to 5.13 seconds. Okay, so any one of them you can actually use. Okay. So the second one, actually I think you could split them also. You could split them also. Okay. So the angular frequency gives us time and frequency. So it's basically just like a 1 point that you can use. Now, okay. Maximum kinetic energy is 9 joules, which can give us maximum the mass of object block is 33 kilograms. And that's it. Okay. On figure 5.4, sketch the variation with h of the potential energy EP of the oscillation. We just actually saw a glimpse. So potential energy would be exactly opposite, reverse of the kinetic energy. So we gonna have the maximum energy would still be at 0.9. So let's use a different color. Maximum energy would be at still 9. Okay. From 0.8 and that was 2. Sorry, 0.8 to 0.6 is 1.4 and then 20. At 1.4 that would be 0. So the curve would be going like this. And that's it. Yeah. Okay. Moving on. You don't actually need this uh, green line, but that's it. Okay. All right. So moving on. Figure 6.1 shows the circuit that rectifies an alternating input voltage Vin and produces an output voltage Vout across the resistor R. So we can see the rectification circuit. 4 terminals of the rectification circuit are labeled WXYZ. Capacitor C is connected in parallel with the resistor R. Okay. State what is meant by rectification. So basically, it's just the process of converting AC signal to DC signal. Rectification is a process that converts AC signal to a DC signal. State the purpose of capacitor. This is easy. This is a smoothing capacitor. It smooths the ripples. Okay. Figure 4.2 shows the variation with time t of the potential differences, PDs, Vn, and Vout. Okay. The variation with Vn with t can be represented by this, where A and B are constants. Determine the values of A and B. Okay. So A is basically the amplitude and B is the omega, that is 2 pi over t. So the amplitude you can see from the maximum and minimum divided by 2. So maximum, minimum divided by 2, it's just 12. So A is 12 volts. B is 2 pi over t, so you need to figure out the time period. So time period can be between two troughs. It could be between two crests also, so 20 milliseconds basically. So time period is 20 milliseconds, so B is omega 2 pi over t, 2 pi over 20 10 raised to power minus. So 2 pi 20 times by 10 raised to power minus 3. This is 314, 310, you could say, radians per second. Determine the type of rectification produced by the circuit in figure 6.1. Okay, now as we can see this over here, that the negative signals are also converted and the ripples are smoothed out. So this is full wave rectification. This is full wave rectification. Okay. On figure 5.3, draw the circuit diagram for the components inside the rectification circuit. Now, there are different ways we can make this design depending on how you prefer it. So, for example, if you prefer that diamond shape diagram, so how that looks like is we will adjust the diamond in a second. So, we can write, and there we go. So, for example, if this is the input signal, sorry, this is input and this is input, another entry for that. So the diodes have to be arranged to provide a specific path for them. And this one, and for this one, it's the other way around. And this one. Okay, and these two will be our output signals. Now, how do we interpret this and how do we understand this? So for example, if this terminal is positive and this terminal is negative, the current will flow through over here. And since it cannot flow through the left diode, it will flow over here, go through the output, come back from this output, and it may look like that this is forward biased, but this path leads to a higher potential. So this cannot happen. Current flows from high to lower potential. So lower potential is towards below. So it will flow this way. On the other hand, if we make this to be negative and this to be positive, the current will flow through over here, same pathway from the output, and this time it will flow this way back to the input wire. So this is one variation of this, which you can actually just copy paste into this. Another way, if you prefer a more like straight, not this diamond shape, you can make it somewhat a rectangular design, somewhat like this. Okay, so again, we would need to clear out some space for this, 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 and this. Okay. So the inputs can be placed over here. This is input and this is input. And these 2 points can be our output and output. So the diode design, so for example, if this is positive, current needs to flow through over here, output back from this terminal, and it cannot flow through this path because again it leads to a higher potential. Current needs to go to a lower potential, so this path has to be forward biased. Now on the flip side, if this is positive and this is negative, so what will happen is that the current needs to go through the same output signal, the same path. It will need to come back from the left side, and now it can go to the input path that we have designated above. So this could be two of the ways that you could actually make it. If you prefer the diamond shape, you can make the diamond shape. If you make the rectangular, if you prefer the rectangular shape, you can make the rectangular shape. So absolutely, there is no problem. So for example, if we make this way, okay, and for that we will have to, even you can rotate this uh, upwards also, this way also. So for example, if this is your output, sorry, this is your input, this is your input. Actually, what we should have done is adjusted the heights of this rectangle, but anyways, okay, never mind. So it has to follow a certain path. So for example, this could be one of the output signals. So it goes to, for example, this way. It goes through Y, comes back through Z, which could be over here, and this could be the pathway that is provided for. On the other hand, if we make this positive and this negative, so the current has to flow through this direction, flow through Y again, come back through Z. Z is over here, and then it needs to flow back through this, back to Z. Now all we need to do is to connect Z over here. So Z can be connected. Since we already have X over here, I don't want to cram more space over there. So for example, Z can be like this. So you can designate this as Z and Y. This is your W and this is our X. A good practice would be to make connection points so that you know that over here the wire is just passing over the stick wires. All right, okay, moving on. Determine a value for the time constant for the discharge of the capacitor C through the resistor R. Okay, so this is the part where the capacitor is active, so we need to see the voltage drop and the time it takes for the voltage drop. So we can see that the voltage drop we can take is 12 and 8. So the V naught can be 12, V can be 8, and the time in which it happens. So this is not exactly 7 and not exactly 8. So somewhere in between and somewhere even towards the left of this. So let's say 2 or 3, 7.2 or 3. That makes sense. So 7.2 or 7.3 you can take. So for example, if we take 7.3 milliseconds, so I think we can use these values. So first we can get tau in milliseconds and then we can get in seconds. Okay, so V is equal to V naught e raised to power minus t over tau. So V is 12, sorry, 8, my bad. 8 equals to 12 e raised to power minus 7.3 divided by tau. So e minus 7.3 divided by tau is equal to 8 over 12, which is 2 over 3. When we take the ln on both sides, we will get minus 7.3 divided by tau equals to ln 2 over 3. Therefore, tau in milliseconds would be minus 7.3 divided by ln 2. It should be ln2 minus ln3 if you remember your rules for exponentials. So minus 7.3 divided by the ln2 divided by 3, we get 1.8. So this is 18 milliseconds. We need this in seconds, so we divide this by 1000. So in normal, I think we can give it into that form also, but 0.018 would be 0.018 milliseconds or seconds, sorry. Okay, moving on. The capacitor C has a capacitance of this. Use your answer in B to determine the resistance of resistor R. Okay, so we know that the time constant is equal to the product of effective resistance and the capacitance. So the time constant we have already figured out. So R would be tau over C. So this is 0.018 divided by capacitance is 570 micro. So 10 raised to the power minus 6. So this is divided by a 570 times by 10 raised to the power minus 6. So we get 31.585. 586, let's call it ohms. So this would be 32. That's it. Okay. Define magnetic flux density. Again, this is a very easy definition, but still let me show you in two different places. Magnetic flux density, force experienced per unit length by a conductor carrying a unit current placed perpendicular to the magnetic field. So basically the force is equal to BIL, that's what we have to, rearrange. And we have this in the formulae and definitions also. So if you see this over here, force experienced per unit length of a conductor in a magnetic field per unit current placed perpendicular to the magnetic field. That's literally just everything we need. So going back, so it is defined as the force experienced per unit length by a conductor carrying a unit current placed perpendicular to the magnetic field. That's it. A particle of mass m and a charge plus q moves at a speed v into the region where there is a uniform magnetic field. The uniform magnetic field is into the page and has flux density B. Particle enters the region of the field at point Y, as we can see. Okay. State an expression in terms of some or all of M, Q, B, V for the magnetic force F that acts on the particle when it is at point Y. So this is easy. This is F is equal to B, Q, V, B, Q, V. Sorry, it's capital Q. Sorry. Q, V, Q, V. Okay. On figure 7.1, draw an arrow at point Y to indicate the direction of force in B1. Okay, so direction of force would be decided by the Fleming's left hand rule, where this is charge, positive charge, so current is in this direction, the middle finger basically. Then we have the magnetic field, which is going into the page. So the force would be upwards. So we just need to do pointing upwards. So that would be this, upwards. So do we need to label it? No, we don't. Right arrow at point Y to indicate. Okay. Uh, on figure 7.1, draw a line to show the possible path of the particle through the region of the magnetic field. Okay, so this tells us that this is going to be a circular motion. Okay, because the magnetic force is perpendicular to the direction of B and the V. So it's going to be a circular path over here. So not the projectile way, the circular path. So it's sort of like a circular path. Okay. Like you could have like a longer radius like this, somewhat like this. Either way, it's fine. Okay. Explain how an electric field can be used with the magnetic field to ensure that the particle in B now passes through point C. So this is the voltage selection thing. So basically what we need over here is that if the magnetic force is going upwards, we need an electric force going downwards of equal magnitude so that the net force FB minus FE comes out to be 0. So we need an equal magnitude of force, of electric force, that would balance out the force on the particle. So that's basically what we need. And if the force or electric force is downward, that means the electric field direction is also downwards. So to ensure particle passes to Z, an electric field or electric force is required that is equal in magnitude to magnetic force acting on particle but in opposite direction. Therefore, the electric field should be directed downwards also. Okay, so with sufficient strength to balance magnetic force or magnetic field. Okay, so you could, however, make that diagram. So electric field, oh, sorry, this is magnetic field. Electric field could be directed downwards. It should be a uniform electric field. This is the electric field. This means that this is going to be plus, this is going to be negative. This is the magnetic field. you could describe the particle also FB and FE, where FB is the magnetic force and FE is the electric force, and net force FB minus FE is 0. Okay. Derive an expression for V in terms of B and electric field strength E. So this is exactly what we are going to do right from this. Sorry. So what we are going to do is that the electric magnetic force is equal to electric force. Magnetic force is BQV, and electric force, remember, is QE. So QE, right? So as you can see probably over here, that Q and Q gets cancelled out, leaving us with BV is equal to E. Therefore, V is equal to E over B. So E over B. And that's it. Okay. State what is meant by de Broglie wavelength. Okay, just to show you that we have the definitions. So, oh, sorry. No. De Broglie, yeah. Wavelength associated with moving particles. State what is meant by de Broglie wavelength. Wavelength associated with moving particle. So, it is the wavelength associated with a moving particle. Okay, calculate the de Broglie wavelength of an electron moving at a speed of this. Okay, so to get this, we have to remember the wavelength equation of the photon. This was h over p. The reverse of that, the reverse of that was the momentum of the photon, h over lambda. So it's basically they're like mirrors of each other. One shows the as you can see, momentum of a photon, although they are massless, but they carry momentum. And this is the wavelength equation of a moving particle. Okay, so now we fill in the values. P is the mv, basically momentum. So h is 6.63 10 raised to power minus 34 divided by the product of mass and velocity. Mass is 9.11 10 raised to power minus 31 kg, and speed is 4.9 10 raised to power 7. So 6.63 divided by 9.11 divided by 4.9 times by 10 raised to power minus 34 plus 31 minus 7. So we get 1.485 10 raised to power minus 11 meters, or 1.5 10 raised to power minus 11. Okay, sorry, this one was separate. State one similarity and one difference between an electron and a positron. So what we can say that they possess the same magnitude of charge, they have the same mass, and they both belong to the same fundamental particle category, which is leptons. So both are leptons, both have the same mass, and both carry same magnitude of charge. Okay, so difference being positron is an antiparticle of electron, and the same magnitude of charge, although we said that they have same magnitude of charge, they have opposite signs. So the charge on sorry, the charge on electron is negative, whereas charge on positron is positive. So you just need one of each of these. Okay. An electron moving at a speed of 4.9 10 raised to power 7 collides with a positron that is traveling at the same speed in the opposite direction. As a result of that collision, two gamma ray photons are produced. State the name of this type of reaction. So this is basically electron-positron pair annihilation. Electron-positron pair annihilation. Okay, state what happens to the electron and positron. So as you can see this over here, this usually is used in the PET scanning. So annihilation is a process where a particle and its antiparticle, in this case electron and positron, collide and convert their mass into energy, typically releasing two gamma. So this is what the annihilation is, what it does. So one more thing happens is that their kinetic energy is also converted. So when electron, sorry, and positron collide, their mass, energy, actually we should say that we should call it rest mass energy, or it's just simply rest. Even if you say mass, that is also fine. And kinetic energy are converted into electromagnetic energy in the form of gamma photons. Two gamma photons, or even if you write plural photons, that is fine. Okay, so moving on. Explain why two gamma ray photons are produced rather than one. This has to do with the conservation of momentum. So when they collide, positron and electron, the Due to that annihilation, the momentum has to be conserved. So there are two gamma photons created which travel in opposite directions. So in order to conserve momentum, two photons are released traveling in opposite directions. Okay, show that the kinetic energy of the electron before the collision is this. Okay, so kinetic energy simply is just half mv squared. If we had the momentum, we could use the half p squared over m also. So half times by mass is 9.11, 10 raised to power minus 31 kilograms, and velocity was 4.9, 10 raised to power 7 whole square. So let's calculate this. So 0.5 times by 9.11 times by 10 raised to power minus 31 times by 4.9 times by 10 raised to power 7 uh, squared. So we get 1.093. Actually, this can be written as 4 also. 10 raised to power minus 15 joules, or 1.1 10 raised to power minus 15 joules. Now, use the information in D4 to determine to three significant figures the wavelength associated with gamma radiation emitted in collision. Okay, so as we said before that the kinetic energy and rest mass energy is converted into two gamma photons. So that's exactly what's happening over here. But again, this was for an electron and positron. So electron and positron mass kinetic energy converted into two gamma photons. So for one electron, we have to go one photon. So kinetic energy plus the rest mass energy equals to photon energy. So kinetic energy was basically what we just found out, 1.1 10 raised to power minus 15 joules. Rest mass energy is the E is equal to mc squared. So 9.11 10 raised to power, oh no, sorry. Oh, yeah, sorry, my bad. Minus and 3 10 raised to power 8 whole squared. Photon energy is the E is equal to hc over lambda. So 6.63 10 raised to power minus 34, 3 10 raised to power 8 divided by lambda. So lambda would be just simply a result of division. So 6.63 10 raised to power 34 times by 3 10 raised to power 8, and 1.1 times 10 raised to power minus 15 plus 9.11 uh, times by 9 times by 10 raised to power minus 31 plus 60. So we get 2.394 10 raised to power minus 12. So this is roughly 2.4 10 raised to power minus 12. Okay, all right, moving on. Question number 9. Define activity of a radioactive sample. So as you can see this over here in the definitions and formulae, it's the rate of decay of radioactive sample. You could also call it rate of decay of the nuclei in a by in a radioactive sample also. Okay, one more thing. We know activity is equal to dA over dt, and it's proportional to the number of nuclei, right? And at the end, its formula becomes A is equal to lambda is equal to n. A is equal to lambda times by n, where lambda is radioactivity constant, radioactive decay constant, basically. Okay, going back, define radioactivity. Define activity. It's the rate of decay of a radioactive sample. Okay. Explain why the variation with time of the activity of the radioactive sample is exponential in nature. So it is pointing out to the fact that activity has uh, this type of relationship. So the reason for that, we already saw this over here, that activity is proportional to nuclei, right? Or activity is the rate of decay of nuclei. So basically, nuclei are decaying. So nuclei are basically decaying. So the graph tangent is already negative. So that's the reason for that. So the nuclei are already decaying. So the decay process actually is exponential. So that's it basically. So we can say is that activity, which is the rate of decay of nuclei, is proportional to number of undecayed nuclei, my bad, undecayed nuclei. So since number of undecayed nuclei is decreasing, the activity also has a decreasing curve. So therefore the they said the activity of a radioactive sample is exponential. Yeah. So therefore it is an exponential decay process. Okay. A sample contains a single radioactive isotope that decays to form a stable isotope. The sample has an activity of 180 becquerels at time t is equal to 0. At a time 8.4 minutes later, the activity is 120 becquerels. Determine the decay constant in per minutes of the radioactive isotope. We wrote the equation already. A is equal to A naught e raised to power minus lambda t. So activity after is 120, activity before initially is 180, and minus lambda t is 8.4 minutes. So e raised to power minus 8.4 lambda is 180 over 120, basically just 3 over 2. So when we take ln on both sides, we get 8.4 lambda is equal to ln 3 minus ln 2, or ln just 3 over 2. So lambda would be ln 3 over 2 divided by minus 8.4. So ln 3 divided by 2 divided by minus 8.4. Wait, sorry. Did we miss out something? Sorry, my bad. I actually wrote it in reverse. This is going to be 2 over 3. So 120 over 180, so that's 2 over 3. 2 minus 3, 2 over 3. So 2 divided by 3, 0.048 minutes, per minute, 0.048 per minute. Okay, use your answer in C1 to determine the half-life in minutes of the radioactive isotope. So remember, half-life is equal to ln 2 over lambda. This is again, actually this is given above in the formula booklet also in the exam. So ln 2 divided by decay constant 0.048. So ln 2 divided by answer, we get 14.36. So roughly you could say 14 minutes, up to 2 significant figures. Okay, on figure 9.1, sketch the variation of the activity A of the sample with T for values of T between T is equal to 0 and T is equal to 24 minutes. Okay, so we said 14 was the half-life, right? So at T is equal to 0, we had 180. So 160, 170, 180, 190. Okay, so it's going to start with 180. So this is going to be our first point, 180. And at 14 minutes later, it should be 90. Right? And I think we can do some intermediate cases also. We also had, in previously we had 8.4 minutes to 120. So 8.4, we need to figure out what this is. So this is going to be 10. This is going to be 9. Somewhere in between 9. So 8.4 would be somewhere over here. So 120. So 110, 120. So roughly over here. So it's going to decay like that. So let's make the graph like that. So let's hope I can make it smooth like that. So on paper, you will have somewhat like this. You can find out where it's at 24 also. So at 24, so A starts at 180, e raised to power minus lambda we figured out to be 0.048. So 0.048 times by 24 minutes. So 180 times by E, sorry, yeah, sorry, this raised to power minus 0.048 times by 24, so roughly 56. So this is 60, so we're not that far off. We can actually keep on going downwards a little bit like this. So that would be 56 roughly. So we can erase a little bit of this. Okay, all right, moving on. Question number 10. State the Hubble's law. So Hubble's law is basically that the velocity of the receding star is proportional to its distance. So we can see this uh, galaxy, the recessional velocity of a galaxy is directly proportional to its distance from an observer. It states that the recessional velocity of a distant galaxy is proportional to its distance from the observer. Okay, a star in a distant galaxy emits radiation that has maximum intensity of emission at a wavelength of 4.62 10 raised to power minus 7. Okay, so basically this is okay. Observations of the galaxy made on Earth detect a maximum intensity of the emission from a star at a galaxy, at a star at a wavelength of 4.91. So basically, this is the original and this is the observations made on the Earth. Okay, explain why the observed wavelength and the emitted wavelength have different values. This is because of the redshift. So the apparent increase of wavelength shows redshift since the star is receding from the Earth. Okay, calculate the speed of the star relative to the Earth. So this is the Doppler effect equation that we learned in A2. So change in difference in lambda over lambda approximately equal to V over C, where C is speed of light. So V would be approximately equal to difference in wavelength 4.91, 4.62. They have the same powers of 10, so that's why we can write it without the powers of 10. divided by 4.62 times by 3 10 raised to power 8. So 4.91 minus 4.62 divided by 4.62, my bad. So 4.91 minus 4.62 divided by 4.62 times by 310 raised to power 8. So this long uh, value, so let's convert it into standard form. 1.88 or 1.9 10 raised to power 7 meters per second. Okay. The wavelength of the maximum intensity of emission is used to determine a value for the surface temperature of a star. So this is the Wien's displacement law. Explain how the temperature determined using this observed wavelength compares with the true value of temperature determined using emitted wavelength. So basically, the Wien's displacement law states that the lambda times by t is constant, which means that lambda 1 t1, lambda 2 t2 is constant. So we know that the observed wavelength is higher than the original wavelength, or let's say for example lambda 2 is greater than lambda 1. So lambda 2 over lambda 1, and this is T1 over T2. So lambda 2 is greater than 1. So this ratio is basically greater than 1, which means that T1 over T2 greater than 1, which further means T1 is greater than T2. So that means that the original temperature is higher. So the original temperature is higher. So observed wavelength is higher than the emitted since you could use Wien's displacement law, since wavelength at maximum intensity, wavelength of maximum intensity is inversely proportional to surface temperature the observed temperature is lower than the original, than the true value or actual value. All right, moving on. A value for Hubble's constant is this. Use your answer in B to determine the distance of the star in B from the Earth. So this is easy. So V is equal to H naught D. This is the Hubble's law. This is the Hubble's constant, H naught. So V we have already figured out. So D would be, we found out the velocity. This is velocity 1.9 10 raised to power 7. And the H naught value 2.3 10 raised to power minus 18. So this divided by 2.3 times by 10 raised to power minus 18. So we get this value 8.187 10 raised to power 24. So 8.2 10 raised to power 24. So that's basically the paper. Hope you liked how I explained. So if you have any questions, feel free to comment. If you want further tutoring, if you want to, if you're appearing for 2026 or even in the October, November 2025, maybe when we are watching this video, that time has already passed. But if you want one-on-one coaching, I've listed the number at the bottom. Do check out the Patreon Grade Booster Pack. Again, the link is you can see in the video. So this is going to be very valuable as I've already shown you multiple different times in this paper. And if you like this video, do give it a like and subscribe to our channel. This means a lot. All right, so see you in the next video. Bye bye.